This is Physics 1B for August 26th, the evening class. And let's get started. We're talking about fluid statics tonight. Just to define what those words mean, you probably know what statics means, but a fluid is basically a gas or liquid. So this is something that we did not discuss in Physics 1A. Maybe someone could tell me why that is. Why didn't we talk about this in 1A? What is Physics 1A the study of? What did we study in that class that came before this one? Gonna run out of Waller. Solids. Exactly. You studied solids. So things like wheels that don't have... They roll, but they don't have moving parts inside of them. Or balls as they fly through the air. Planets as they move through space. Objects that don't change in shape in any way. So fluids behave a little bit differently. But we can talk about the behavior of fluids, whether it be a gas or a liquid. I guess when I was a kid, the word fluid to me always sounded like liquid. I don't know, but it's either gas or liquid. There's differences between these two things. Liquids basically tend to take on effectively kind of a fixed volume. And this is due to the fact that, just as an example, volume. If I take a glass of water, right, it has a certain shape to it, a fixed volume as well. If I then take that water and I pour it into a pan, it'll kind of spread out in the pan, occupying the same volume, but just taking on a new shape. So the shape is not fixed, but the volume of the liquid tends to be fixed. You can obviously take a glass of water and spill some out, and the volume changes, but that's not what I'm talking. I'm saying that if you take a fixed amount of liquid, it's going to have a certain amount of volume. A gas, on the other hand, has no shape that's defined and no volume that's defined except by its environment. I can blow air into a balloon, right? And it takes the shape of a balloon. But then if you let open the end and you let the air flow out, it'll just kind of fill the room, just spreading out throughout the room. So the gas tends to not have a fixed volume, or a fixed shape for that matter. So that's what we want to discuss today is how fluids behave, and in particular how they behave in static situations when the fluids themselves are not moving. So in order to do that, we need to kind of define some terms that you may or may not be familiar with. The first one is density, right? So density, let me get to a position where I can write a little better here. So density is basically just defined as mass divided by volume. You've probably used this in classes before. That's probably not a new thing to you. How you use this in other classes, I don't know what symbols you used. I maybe used D, but in physics we're going to use the Greek letter rho. That's the symbol that almost all physics textbooks use. For mass, we use the symbol M, of course, and for volume, we use a capital V. But that's our definition of density. The units that we use for this. There's many different kinds of units, but the one kind of we most commonly use is kilograms per meter cubed. And a common density that we need to use specifically in this class is the density of water. The density of water has a really simple value. Maybe some of you know what it is. It's 1,000 kilograms per meter cubed. You can convert this into other units, but the density of water is about 1,000 kilograms per meter cubed. All right? We'll use this a lot. It's the kind of thing that when you're doing your homework, you need to remember this is something that you just need to know, basically. It'll come up quite a bit. In other forms of units, I believe this is also about 1 gram per centimeter cubed. Do you guys know why it is that water has such a specific value of 1,000, exactly 1,000 kilogram per meter cubed, or exactly 1 gram per centimeter cubed? Do you guys know why that is? Because we set it that way. We didn't get lucky, it's because we set it that way. So the original definition of a kilogram was you basically take a cube. So let's say you have a cube. you take a cube, and I'll just fill in the other sides here. So you got this side, this side, this side, this side. If you make that cube such that it's a cube with each side being exactly 0.1 meters, so 0.1 meters here in terms of height, depth, and width, it's a cube, right? So every side has to be exactly the same. And then you fill the entire thing up with liquid water, all the way completely filled with water, then that's going to be 1 kilogram of water. And that is how the kilogram was defined, actually. The kilogram was defined based on water, which is why, you know, you get 1,000 kilograms per meter cubed. The volume of this object, right, this would have a volume that would be equal to 0.1 times 0.1 times 0.1, right? So 0.001 meters cubed. And so you can see if 1 kilogram fills up that volume, you need 1,000 kilograms to fill up something that's a meter by a meter by a meter, right? Okay, so that's our definition of density. And different objects have different densities. Something like gold, for example, which we'll talk about later, has a density that's on the order of about 20,000 kilograms per meter cubed, about 20 times the density of water. Something like lead is somewhere in that same region. I think copper is something like 9,000 kilograms per meter cubed. You may have done experiments in chemistry, experiments in physics 2A, where you did things like measure density, probably. So that's something we need to understand fluids. We need to be able to use this language of density. Okay, and we also need to be able to kind of like see this equation in another way. A way that we're going to commonly use that equation is to rearrange it, multiply the volume to the left-hand side, and say that we can define mass as simply being the density of whatever substance we're talking about, and we multiply that times volume. Okay, so that's an important equation that we'll be able to use in this class. All right, any questions? All right, gases tend to be much less dense, so if I look up, for example, the density of air at different elevations, the density of air, I think at sea level, is something like 1.2 kilograms per meter cubed. So that's a factor of 1,000 less than the density of water, which goes to show you that the molecules of air are significantly more spread out than water. This is because inside of liquids, there's kind of internal forces that keep the liquid molecules close to one another. Okay. All right, so let's move on. Let's define what pressure is. And the goal here is to just define these terms so we can use them to solve and understand other systems, like to understand like how a hydraulic press works. So for pressure, now we're talking about fluid pressure. Pressure is defined in a very simple way. It's basically just, we can put an equal sign here. Pressure is basically a force that's exerted over some type of an area. All right. The units we use for this, or the symbol, would be P equal to force divided by area. And the unit would be, you know, a Newton divided by a meter squared. That's the unit we can use for pressure. And we give this a name. Maybe you guys, does anyone know what the name of this is, if you happen to read? I'm sorry, I don't have any water, and my mouth's going to get dry really quickly here, so. It's a Pascal, that's right. I apologize. I'll be back in one moment. Okay, apologies. Yep, that's a Pascal, as he said. 1 Newton per meter squared is equal to 1 Pascal. And instead of calling it 1p, we do 1p with a little a down here. That's a force of 1 Newton spread over 1 meter squared. Okay. There's other units of pressure, though, that you guys probably know about. Do you guys know about other units of pressure? What's one that you use in your chemistry classes if you've taken those? What kind of pressure unit do you use there? mmHg is 1. Yep, so that's a unit. Millimeters of mercury. Okay, let me undo that. Undo. So mmHg, that's 1. And then atmosphere, and then bar. Yeah, exactly. The bar is directly related to the Pascal. I'm going to put a little relationship here so we can see what the conversion factor is going to be. That is supposed to be an equal sign. It doesn't look like one, so let me fix that. So one atmosphere is directly related to pascals, and then torr is another one, yeah. So I'm just going to talk about atmospheres and MMHGs. One atmosphere is something like 760 millimeters of mercury. This is defined based on something called the barometer that we'll talk about that we use to measure pressure. And then in terms of pascals, this comes out to about 101,300, so 101,300 pascals, or newtons per meter squared. So there's kind of some relationships right in there. A bar is related directly to this number, although off the top of my head I don't know what it is. So those are different measurements and units that we can use for pressure. Okay? But then, what exactly is pressure? Like, what is it and why do we care about it? So if you take a fluid, a vessel with some kind of fluid in it, you know, for example, let's say you have you've got a vessel and it contains water, right? And let's say within this water we put a shape. Okay, so we're going to put a little diamond in here. We'll make it black. So we put a little diamond inside a water substance right here, and this is, let's just say this is like it's a two-dimensional object just to keep things simple here. So the idea of pressure is that the water molecules that are in this fluid, right? They're constantly kind of moving around, and they zip in and they zip out. They bounce off the side of this, and they continually exert forces against the surface here. And the forces they exert are kind of always just kind of perpendicular to the surface at all points on the surface. Now, the amount of pressure that this object feels is, you know, it's not the same everywhere. The deeper you go into the fluid, the pressure gets higher. But we can kind of say that force that acts perpendicular to all surfaces of the object is going to be dependent upon what the pressure is at that location in the fluid, multiplied by the area. So in principle, that would mean that the pressure down here on this side and on this side here would be higher, and therefore this force here would be bigger. But the only thing I'm trying to represent with this is to say that you feel force on all sides of an object that's submerged in a fluid. You can feel this yourself if you have a sink, like your sink in your kitchen. You fill up water, or you fill up a bathtub, or you put your hand into a pool or something like that. When you put your hand into a fluid, you feel pressure on all sides, right? You feel extra pressure from those water molecules bouncing off of you. And it happens on all sides, basically. We also feel pressure from the outside. If there wasn't external atmospheric pressure, then this water would just evaporate out, right? So there's also additional pressure that exerts down like this that we would call kind of like atmospheric pressure, the pressure of the atmosphere. And that 1 ATM, 1 atmosphere of pressure, is basically the air pressure that's exerted at sea level. And this even has a name. This has the name of, we call it kind of P naught. That's the symbol that a lot of textbooks use. This is the pressure at sea level of the air. And that atmospheric pressure, it pushes down on the top of this fluid, which means you've also got, you know, there's a downward force on this fluid right here that acts due to the atmospheric pressure. All across the top of it, you've got forces that are acting down. Okay, the size of the force is dependent on the size of the opening here and on the area. Okay, that atmospheric pressure, like where it comes from, actually, and we're going to see this almost immediately in the next step, is Archimedes figured out that pressure is produced. Maybe you guys can tell me. Do any of you guys know, where does that atmospheric pressure come from? Comes from air, obviously, but why is it, for example, that atmospheric pressure is, well, tell me this. If you go to the top of its gravity, that's the right answer. Yep, it's basically the weight of all the air. That's what you're feeling when you feel air pressure. And we'll prove that very quickly here in a second, with specifically talking about water. When you go to the top of a mountain, what happens to air pressure? Does it go up or down? Go to the top of a mountain, is the atmospheric pressure less than an atmosphere, more than an atmosphere? What happens? It's less, right? Yeah, exactly. And why would that be? Well, you're higher up in the atmosphere, so there's a lot less air below. There's less air above you, and there's more air below you when you're on top of a mountain. So there's less weight of air, and therefore there's less atmospheric pressure. Now, atmospheric pressure can be affected by things. It can be affected by, the amount of water in the air can affect the atmospheric pressure, because the amount of water vapor would increase uh, the pressure, and we can measure this with things like barometers. Okay, you guys have to tell me, can you see the motions of my you can? Okay, good. I just can't remember if it shows up on the recording or not. I feel like it doesn't show up on the recording. We'll see. I just can't remember. I think for some reason it doesn't. Okay, I think that's all I have to say about pressure. Do you guys have any questions? This is something you've probably experienced in a lot of your classes, but if you do have questions, please feel free to ask. Because we're going to, we defined a couple things, and, just like in all physics classes, we're just going to kind of jump up in difficulty real quick here. Okay, what's next? We got through 1 and 2. Now we're going to spend quite a bit more time on these 3 here. So this is the next thing we want to talk about. Variation of pressure with depth. And if you do have a question, feel free to keep typing. Okay, that's interesting. We will talk about that, Carlos, during the break. I'll pull open OBS and we can fix that. Thank you. Okay, variation of pressure with depth. All right, so what is this? This is the idea that if you were to go into a swimming pool or into the ocean and you swim really far down, like let's say you go to the bottom of a 10-foot deep pool, what do you feel? And where do you feel it? What do you notice when you swim to the bottom of a pool? What feels different? Your ears. Maya says your ears. That's right. What do you notice about your ears? You feel pain in your ears. And that's due to, as Arya says, more pressure. That's right. So we already have a sense of understanding that the deeper you go, you feel this pain in your ears. And that pain, I'm going to tell you now, is due to pressure. It's due to increased pressure the deeper that you go in the water. So we want to understand why that happens. So in order to do that, we're going to draw a vessel that's going to contain some water. And within this vessel, so we've got water in here. Okay, so you've got just plenty of water. And out of this water here, we're going to select a kind of column of water. So we're going to say that this water is still. It's still water. It's not really flowing around too much. Now the molecules are moving for sure, but en masse, the water is not moving, okay? And so what we're going to do is, out of this water, we're going to take a cylindrical column of water. Kind of an imaginary, static, cylindrical column of water that has an area on one end over here that we call A, an area on the other end that we call A, and then a height, H. So that thing there is basically just a column of water inside the water. We're just kind of like bracketing out some of the water and saying this is the piece of the water we want to look at. And in particular, of that water right there, we want to look at the forces that are acting on it, okay? So in order to do that, what we're going to do is we're going to say, let's say at this location right here on the top, okay, that all along that one level right there, that we go and we measure the pressure, and we call the pressure at that point, let's call it P1. Now let's call it P2. And then we go to the bottom of our object, and we say the pressure on the bottom of the object, we're going to call P1. And they're different from each other, and we're going to work off the assumption that what we said is true, that basically the pressure below P1 is greater than the pressure above P2. And then we're going to say, well, if the pressure at this location is P2, then we know that there's a force at that location too, right? So acting down, because the pressure acts downwards on this top surface, because it has to be perpendicular to the surface, it's kind of like the normal force, there's going to be a force that I'm going to call, we'll just call it F sub 2. And we can basically say from before that force has to be equal to the pressure multiplied by the area. The pressure at that point is P2. The area of the top is A, so you get P2 times A. On the bottom, we're going to say, well, there's going to be a greater force, right? So we'll draw a longer vector and say on the bottom right here, we're going to have a force, and we're going to call it F1 and say that it's equal to P1 times A. Right? The pressure on the top, the pressure on the bottom. Now we're imagining that this column of water here is static, it's not moving, and it's going to have one more force. What other force would this object have? This column of water sitting inside of here? Gravity, yeah. So we'll also add into here that there's a weight that points down this way. Okay? So we've got our weight W, our forces on the top and the bottom. So you guys tell me now, if this is a static situation, how are these three forces going to be related to each other? Oh, I left something out. There's also going to be forces on the sides, right? I mean, after all, I told you a second ago, when I have an object that's submerged in a fluid, there's forces on every single side. It's a cylinder, so there should technically be a force coming in from the screen. There should also be a force this way, right? And there should be a force this way. Yeah? What about those forces? Do I need to worry about the forces on the left and right? What do you guys think? If I go to a specific level, they should cancel. Yeah, exactly. You're going to have a force on the left and a force on the right at every location. And the forces on the bottom will be a little bit bigger than the forces on the top, but they're balanced out completely by the forces on the sides, right? So we're just not going to worry about those. We'll just undo that. So you don't have to worry about those. They exist. We're not worried about it. So how do I want to relate these three forces to each other? How could they possibly be related? What kind of thing that you learned in Physics 1A would relate those three forces to each other? Yeah, that's exactly right. They should add up to 0. Now, we need to define a direction to be positive, right? So let's just make the common convention. We'll say the positive y direction points to 0. And we can then say that, let's see, the upward one is this one, right? So that would mean that basically we sum up all the forces acting in the y direction. Those should add to 0. So what do we have? We've got F1 minus F2 minus W. And those are all equal to 0, right? Or as Kwong Win said, that means that F1 equals F2 plus W. I'm going to leave it in this form. F1 minus F2 equal to W. And then we're going to start making some replacements. Now, before I continue, do you guys have any questions? We're just going to kind of make some replacements here with formulas. Do some algebra, and we'll get to the answer. All right. So F1, we said, was P1 times A. And F2, P2 times A. That's equal to the weight. How do we normally do weight? Well, we say it's equal to the mass of our object multiplied by gravity, right? But what about this? How can I rewrite this? Well, we said before that we can define mass as being equal to... Does someone want to answer? Chris is going to type something. How could I change the way that mass is written? Density times volume, exactly. So if we took the density of our fluid, which is water, and we multiply by volume, that would give us the mass. What about the volume? How can I rewrite the volume based on the picture that I drew here? Is the volume related to any of the other things in here? Maybe the area, for example? Is there a way that I can write the volume height times the area? Exactly. So if I take the area times the height, that is the volume, right? It's the same thing, because the area of the cap is A, it has a height H, and it's a cylinder. So you get that, you get the volume, right? So that means that I can replace the mass in this equation as, and this is going to be something that's going to kind of, well, I'll stop this. mg equal to rho times A times H, all of that's the mass, and then that's multiplied by G. The left-hand side of the equation, we can factor out the area so that it says P1 minus P2 multiplied by the area is equal to rho, I'm going to rearrange these just a little bit, GH, so density of water times gravity times the height, and then we have this area sticking over here. Should be able to see pretty quickly that these areas cancel. And what we're left with is the relationship of how pressure varies with depth, which is really quite simple. The pressure at the lower point, P1, minus the pressure at the upper point is equal to basically the density of the water multiplied by gravity and then multiplied by height. That's the difference in pressure that you get. And you can see that it's dependent upon gravity, which is exactly the reason, like I asked a second ago, where does air pressure come from? And someone, correctly responded that it comes from gravity. And you can see here that it is the gravity of the water, and then there's the density of the water that's actually creating it. Now, this isn't usually the most common form this is written in. Often what people do is they redefine this relative to the surface. Okay, and the reason why they do that is because we know at the surface what the water pressure is. So if I were to reconstruct my same system, and I said, suppose that I come down here to some point, and we call that point, and we say the pressure is P, and then we say at the surface that the pressure is P naught, and we define this height here to be H, then a simple relationship we can construct out of this, P becomes P1, P naught is at the surface, right? And the other stuff stays the same. So the relationship we end up getting out of this, which is the most general one, I think, we'll put it in a different color, is that the pressure at any point in a fluid is equal to the pressure at the surface, okay, so we add the negative P naught to the right-hand side, plus this rho GH here. And that is, I think, the most common form you're going to see in a textbook, or if you look up how pressure varies with depth. This one tells you the difference in pressure between 2 points. That one kind of tells you the pressure difference between the top. Keeping in mind that P naught in this case, again, that represents, if it was on Earth, it'd be 1 atmosphere of pressure. If we're on a different planet, it's going to be whatever the atmospheric pressure on that planet is. 1 atmosphere at sea level, of course. And there you go. That is a kind of mathematical description using stuff you learned in 1A about static fluids that tells you how you can get more pressure the farther you go down. Okay? We'll do some problems to kind of verify that you guys are understanding what we're saying here, but does this make sense to you guys? All right. So let's ask some questions about this to like kind of just and then we'll do a problem. So what if we wanted to ask this question? I'll just type it when I write this stuff. What if I wanted to ask this question? How deep would you need to go to reach a pressure underwater of 2 atmosphere? How deep underwater would you need to go to reach a pressure of 2 atmosphere? Does anyone know what the answer is? Like right off the top of their head? Maybe somebody already knows. If you don't, it's okay. Or if you have a question, if you're typing, feel free. So how would we figure that out? We want a pressure of 2 atmospheres, right? So let's use our equation here. So we would say 2 atmosphere should be equal to, well, you know what? Let's use that equation. So 2 atmospheres minus the pressure at the surface should be equal to rho GH. Well, what was rho? What's rho again? Someone remind me, what's rho? It's density, but density of what in this case? Yep, so 1,000. It's 1 kilogram per cubic meter. G is obviously 9.8. And then H, that's what we're trying to solve for, right? What is H, right? We're trying to say, what is H equal to? Okay, now, if I was to take the left-hand side, it looks like it's 1 atmosphere, and if I divide it by 1,000, okay, 1,000 times 10 is like 10,000, right? We would get an answer of 1 atmosphere divided by 10,000 things. We get a really tiny number, right? So we kind of need to do something here, right? Atmospheres are not an SI unit. Okay? So you can't simply divide these type of units on the right-hand side underneath atmosphere. So instead what we have to do is we need to convert that over to pascals, because pascals is an SI unit, right? So we would convert this to 1.013 times 10 to the 5 pascals. And then we can divide by these two. And we'll get an answer. The answer should be pretty simple. What do you guys get if you calculate that? You can kind of check for yourself if these units work out here. Oh, I left something out. This is per meter cubed. I was looking at the units and they didn't make any sense. Yeah, thank you, A.B. Gomez. What do you get as an answer? Feel free to like just type an answer in the chat, by the way, if you got an answer already. Don't be shy. Even if you get it wrong, it's not a big deal. We're here to learn. You got about 10, right? 10.3. Yep. That's right. So that tells you that every 10 meters that you go, you add another atmosphere of pressure, right? So if you go down to 20 meters, how much pressure would you feel at 20 meters in terms of atmospheres? Or technically 20.6 meters. 3 atmospheres, right? And 30 meters, you're at 4 atmospheres, right? So, there you go. Now, I've never been this deep in the water. Maybe some of you guys have, I don't know. 10 meters is like about 33 feet or so, right? So that's really, really deep. But if you've been scuba diving, then you've probably gone that deep before. Yeah. Okay, so there's variation of pressure with depth. Do you guys have any questions? I'm gonna have you guys do a problem now. Here it is. I'm gonna say one more thing about this before we do it, actually, though. Okay, so the derivation that I went through right here is a pretty common derivation you can see in textbooks. If you go back and look at the derivation in your textbook, I think it's kind of confusing, personally. I don't really like it very much, but I will kind of point one thing out that they say that is relevant to us here. If we look at this equation right here, and we kind of reframe it in the following sense. So if we go back to our picture, and let's say that we define the y-coordinate right here to be y sub 1, and we define the y-coordinate up to point 2 to be y sub 2. Oh, excuse me. Then we could say that in our system right here, I just want to erase this piece. So in our system right here, we could say that y2 minus y1 would be equal to h, right? And we can substitute that into our equation here. You'll notice that the P1 over here and they're kind of like inverted. So what we can do is we can rearrange this a little bit by factoring a negative sign out of the right-hand side so that it becomes P1 minus P2 is equal to negative rho G like that. Just all I've done is just rearrange these two. And then what we can do is say, well, P1 minus P2, that's kind of like the change in pressure as you go down, right? And on the right-hand side, you've got negative rho G, and then Y1 minus Y2, that's kind of like delta Y, right? And then we can rearrange it so that it says the change in pressure with respect to the change in depth is equal to negative rho G. And then what your book does is they take the limit as delta Y becomes really small, and they turn this into a derivative. Now, this is how they start the chapter. They start the chapter by giving you this equation and saying this is how pressure varies with depth. I think that is a really complicated way to introduce this, and I hope you think that this equation is a little easier to understand. That being said, at some later date we will start using this with more complicated problems. Okay? I don't have corona, but that's maybe funny. Okay, so you can look this up in the book. It's it's just a more complicated way to derive the same thing. All right, so here's what I want you guys to try to do. So here's an example of a kind of problem that you might have on your homework. So it says we want to estimate the force exerted on your eardrum due to water when you're swimming at the bottom of a pool that's 5 meters deep. Okay? And so let's just kind of draw a picture here. I'm going to give you guys like 5 minutes to solve this. If you already think you know what to do, go ahead. So we've got our pool. Here's the surface up here. We know that it has a height that's equal to 5 meters. I'm going to rewrite our equation down over here, which is that if the pressure at the surface is P naught, then the pressure at a lower point is going to be equal to P naught plus rho GH. And what you're supposed to figure out is, suppose that you're lying down here at the bottom. You're going to feel pressure on your eardrum here. And specifically, we want to find force. Okay? So there's going to be a force on your eardrum here. And that is what our question is. What is that force equal to? All right? Now there's more to it, which this is something that's important to understand. It says the air inside the middle ear is normally at atmospheric pressure. Therefore, to find the net force on the eardrum, you have to consider the pressure difference between the total pressure at the bottom and atmospheric pressure. So this actually tells us something. Oh, and then let's estimate that the surface area of the eardrum is about this. This tells you something, before we get started on this, about something you've probably experienced before. If you go down to the bottom of water and you feel this force, you can kind of fix that in a way. You can kind of remove the force, right? How can you do that? And if you don't immediately know the answer to that question, if you've ever driven up a mountain and you started to feel something similar, like a pain in your ear as you drive up the mountain, you can chew gum. That's one way to do it. Yep. How else can you do it? You can pop your ears. So popping your ears, chewing gum basically pops your ears. Yawning will also pop your ears. So what effect do you guys think that has? Why does it work? This problem is kind of all about that idea. What happens when you chew gum or pop your ears? I don't know if chewing gum at the bottom of the pool will work. It lets the pressure equalize. That's exactly right, Brandon. It lets the pressure equalize. So I think about the example of like getting on a plane, the plane going up. As you go up higher, the pressure in the cabin drops, and the pressure inside your ear stays the same. But what I do is like hold my nose and blow into my nose, and it like pops your ears, right? What it does is it like lets air either in or out to equalize the inside pressure and the outside pressure. And when they're equal, you don't feel anything. When they're equal, you don't feel anything at all. Okay, so see if you guys can solve this problem. Read carefully what this says. Okay, and see if you can figure out what the force exerted at the bottom of a pool that's 5 meters deep is, given that the area of your eardrum is this. I'll give you like 5 minutes or so to figure it out. We'll come back and we'll talk about this in about 5 minutes. If you do get an answer, feel free to put it in the chat. But think about it. Oh, I missed the person who said, Maya said, adjust the pressure in the ear and the tympanic membrane. I don't know enough about biology, but that sounds correct. That sounds exactly right, too. I didn't see that one. When you do get an answer, feel free to put it into the chat. And again, don't be afraid if you don't know if it's right or not. It's okay. Just take a guess. I mean, type what you think it is. Okay, one person answered. give you guys like one more minute. Okay, I'll say that the two people that answered are right. And I guess we can go through and talk about why. The main thing here is that inside the eardrum, you've already got a pressure that's equal to atmospheric pressure. So to find the pressure, the extra pressure that you're feeling, you kind of need the difference between the external pressure and which is P, the pressure at the bottom, and the pressure at the top, which is P naught, or the pressure inside the ear, sorry, which is P naught, the same thing. And according to that equation, that's equal to that. And then we also know that the force is going to be equal to that pressure difference multiplied by the area of the ear. So if you plug all these things in, plug all the numbers in at least, you end up getting, you know, density is the density of water. G is acceleration due to gravity on Earth. H is 5 meters, the depth of the pool. And then the area of the ear is this right here. And you put all that together and you get about 4.9 newtons. Or 5. Alright? Does that make sense? Anyone have any questions? Okay, in that case, I'm going to stop this recording, and we're going to have a short break. And when we come back, we are going to talk about take into consideration weight. Okay, before I do that, I'm going to answer this question. So I thought we should take into consider the weight of the person. So we were interested in finding just the force on the eardrum itself. Okay, so the person definitely has a weight, and it's good to think about using weight in this case. But that weight is just, you know, the force of the mass of the object in the gravitational field. So it's like they feel weight, but the eardrum's not feeling that weight, if that makes any sense. Yep. Good question. Okay, so I'm going to pause the stream.